This is Lulworth Cove in Dorset, one of the best-known areas of British geology. The structures are clearly compressive, and geologists have always wondered how they fit into the context of pervasive extension throughout the Mesozoic and Tertiary history of Northwest Europe. Is this the leading edge of alpine compression? If so, how does it fit into the earlier extensional regime which existed?
Compression usually generates anticlines, and what we see here is indeed the front limb of a large anticline.
So, whatever mechanisms are acting, they seem capable of producing significant hydrocarbon traps. It would pay us to know more about structures like this. Field geology and seismic interpretation are our traditional approaches to these problems. And indeed, where the data's good, these techniques in combination can give us a very reasonable picture of the structure as it is now. But to help us understand how the structure's developed, and also to help us in places where the seismic data is less clear, we need to create a model of the processes involved. One way of doing this is through analogue modelling using sandboxes.
An earlier video showed how work done at Royal Holloway and Bedford New College, London, has helped us to understand the complex geometries caused by extensional faulting in the Earth's brittle upper crust.
This video shows how compressive structures are formed after an extensional phase, and that requires modelling the process known as inversion. The term inversion is surrounded by confusion in the geological literature. To explain what we really mean by inversion, Mark Cooper.
The early concept of inversion was that of an inverted basin, a basin that has become a structural high. However, the concept is now applied not merely to the basin, but also to the fault system that controls basin development, as shown in this simple cartoon based on the work of A.W. Bally. In this illustration, the pre-rift sediments are shown in blue, the syn-rift sediments are shown in red, and the post-rift sediments are shown in green. Inversion structures, such as these, are most commonly observed in intracratonic settings. However, inversion structures are also recognized on passive continental margins, within orogenic belts, and on active continental margins. The inversion structure in this diagram has an exaggerated geometry and is therefore easily recognized. However, in real examples, the geometry is more difficult to see, and so we have to use the concept of regional elevation. Regional elevation can be defined as the normal, undeformed elevation of a chosen marker bed, for example, the black bed here. An extensional fault will lower the bed below regional, causing omission of the stratigraphy, such that a well A drilled in this location would not penetrate the marker bed at all. A contractional fault, by contrast, would elevate the marker bed above regional, and a well drilled in this position would penetrate the marker bed twice. The key to recognizing an inversion structure is to see marker beds with different elevations to their respective regionals. Some beds will be elevated above their regional elevation and in net contraction, whilst other beds will be lowered below their regional elevation and be in net extension. The zones of net contraction and extension on the fault will be separated by the null point. The null point is initially near the top of the syn-rift package, but with continuing inversion, the null point migrates towards the base of the syn-rift sediments. Another important factor in the recognition of an inversion structure is the reuse of the old extensional fault system during the inversion process. Commonly, when an extensional half-graben is inverted, a footwall shortcut fault may develop, creating a more gently inclined fault trajectory that is more favourable to accommodate the compressional stress. The shallower dipping footwall shortcut creates an efficient trajectory for the shortening that is required during the inversion process. Clearly, there is the possibility that during the inversion process the extension faults will not be reused at all, and a new set of faults will develop to accommodate the contraction. The substantial reuse of the old fault system should be a prerequisite of the inversion process. The models in this film are designed to illustrate the possible structures that can originate from inverting a wide variety of original extensional geometries. It is these processes that have been modelled by Ken McClay.
The model is first extended to produce an extensional architecture and then compressed to produce the inversion structures. Testing of faulted sand shows that it is weaker than unfaulted sand, and as such we would expect faults developed during extension to become reactivated during compression if they are suitably oriented. Extension is achieved by moving the end wall back at a constant displacement rate. During extension, syn-rift sediments are added incrementally. At the end of extension, we add a post-rift sequence and then compress the model by moving the end wall back. Repeated experiments have shown that the results are very reproducible. During both the extension and inversion phases, we monitor the deformation using still photography and time-lapse cinephotography. The time-lapse sequences form the basis of this film.
The first model is a simple listric fault with a fixed footwall geometry. The pre-rift sequence is alternating layers of white, blue and black sand. As extension begins, the hanging wall is pulled away from the footwall. The hanging wall then adjusts to accommodate the shape of the main fault surface. A crestal collapse graben forms in response to arc stretching. The crestal collapse graben is bounded by synthetic faults, which dip in the same direction as the main listric fault, and by antithetic faults, which dip in the opposite direction. The synthetic faults are steeply dipping when first formed, but quickly rotate to lower angles during continued extension and become convex upwards. With further extension, new faults form in the centre of the crestal collapse graben. During extension, the void is infilled with red and white syn-rift sand layers. The void in the hanging wall is completely filled to the top of the footwall block, the regional elevation. Sedimentation exactly keeps pace with extension. At the end of 20% extension, a post-rift sequence of green and white sand layers is added. The model is now inverted by moving the right-hand end wall back. This reactivates the main listric detachment, and a shallow thrust verging towards the footwall propagates upwards into the post-rift sequence. Deformation is now taken up on a steeper thrust. Two further small footwall vergent thrusts propagate upwards from the tips of synthetic extensional faults in the crestal collapse graben. Two hanging wall vergent thrusts propagate upwards into the green and white post-rift sequence from the tips of antithetic extension faults. Notice that none of these minor thrusts actually reactivate the pre-existing faults which remain extensional. As the inversion continues, a new hanging wall vergent thrust fault propagates upwards from the basal detachment. The model is uplifted asymmetrically above the reactivated main detachment. At the end of the inversion, the model has been returned to its original pre-extension length. The syn-rift sediments have, however, not been completely expelled out of the half graben, but part remain in extension below regional. The resultant geometry of the syn-rift wedge shows a characteristic arrowhead or harpoon structure, caused by the rotations with opposite senses during both extension and inversion. We can compare this model with a seismic line across a basin in Indonesia, remembering, of course, that seismic lines are not geological sections. The vertical scale is reflection time. The asymmetric anticline at the left is very well developed. This is also the area where the red-coloured syn-rift deposits abruptly change thickness. We interpret this as the basin boundary fault, though we cannot seismically pick a single major fault. The sediments on the shallow dipping limb of the anticline show the polarity change that is characteristic of inversion. the pre-inversion sediments thicken to the left towards the anticline crest, while the post-inversion sediments thicken to the right. Below this zone we see a small graben, probably a crestal collapse feature that has not been affected by inversion. Moving across the basin, there are other minor faults, some reversed and others not. Here, there are two clear inversion structures, both much smaller than the main inversion anticline. These have divergent polarity. The thickness changes in the Sin Rift deposits show that this was a shallow graben, and it is the main faults on both sides of the graben that have been reversed. This looks like the inversion of a crestal collapse graben as modelled, but we cannot see whether fault reversal is confined to the shallower strata, with the deeper faults unaffected, as in the model. The second model is a simple planar fault that links to a horizontal detachment. As in the Listric fault model, extension is achieved by pulling the hanging wall away from the footwall. The first formed fault is a strongly curved synthetic fault that has extensional displacement at the base and reverse displacement at the top. The fault has this geometry because the block to the right is rotated, whereas the block to the left is simply lowered. As extension proceeds, an antithetic fault forms and propagates down to the point where the main planar fault joins the basal detachment. With increased extension, a crestal collapse graben develops. A second, strongly curved synthetic fault forms in sequence towards the main planar detachment. Sin Rift, red, white and black sand layers continue to be added incrementally during extension. A series of smaller synthetic faults form as extension continues. After 20% extension, movement of the end wall is stopped and a green and white post-rift sequence is added. At the start of inversion, the hanging wall moves back from the right, reactivating the main detachment and uplifting the central section of the model. A footwall vergent thrust fault propagates up into the post-rift sequence from the main detachment. On the right, hanging wall vergent thrust faults propagate from the tips of the crestal collapse graben antithetic faults up into the post-rift layers. The central part of the model is now uplifted in a large pop-up structure. Starting from the king point in the main detachment, a new hanging wall vergent thrust propagates in sequence and upwards. At the end of inversion, the model has been restored to its original pre-extension length. Note, however, that the Sin Rift sediments have not been totally pushed out of the half graben, but remain, in part, below regional. This seismic line, also from Indonesia, shows some of the features of inversion of a planar fault basin. There is no major rotation of the graben fill, either during extension or on inversion, although the thickness variations are considerable. The only minor fault block that does show rotation is in the same position as in the experiments, the horst between the main graben and the crestal collapse graben. To achieve this rotation, the faults bounding the horst must be curved and steepen downwards. These are not fault shapes that most seismic interpreters expect, and it is only with the insight provided by the model that we can confidently make this interpretation. Most of the rotation of the block occurred during extension, but we can see from the deformation of the post-rift beds that the upper, reverse part of one of the faults was active during inversion. The models, structures and their application to seismic interpretation are discussed by Mark Cooper, Ken McClay and the head of BP's structural geology group, Chris Banks.
Yes, I think it's interesting to me, at least, to see the partitioning of the deformation between the characteristic asymmetric anticline developed above the main controlling fault. We can also see small compressional structures being developed above the crestal collapse graben. Some of these clearly relate to the old extensional faults, others appear to be newly developed. There are also other structures in here due to the inversion. We can see one just starting to develop in this model, but it's much better developed on this other model with the planar fault, where we can see a prominent back thrust that cuts all the way through the stratigraphy and takes some of the displacement up the rollover of the model.
Yes, this partitioning between the structures on inversion creates some distinctive families of structures. At crustal scale, these could extend over perhaps 50 kilometers or more. And I think models like this may help us recognize the genetic linkages of these types of structures. Another thing that interests me is the way that shortening is distributed between the asymmetric anticline on the footwall side of the basin and the thrusting that occurs on the hanging wall side. For example, in a basin that I've recently been working on in Syria, using outcrop seismic and well data, there is almost no reversal of the two main basin boundary faults. But the other features of the Listric model are well represented. The central domal uplift above the crestal collapse graben and a small thin-skinned thrust zone.
In this example of a previous Listric inversion model, we have a situation whereby the main extensional fault has not been reactivated, and instead we have deformation concentrated on this main thrust system here, folding of the hanging wall, and a small amount of deformation on this thrust system coming out of the crestal collapse graben. In this situation, we have a strain gradient which progresses towards the footwall, and it has not reached the main extensional fault and hence has not reactivated it. This leads us to the problem of describing the polarity of such inversion systems. In this situation, we have vergence towards the hanging wall and a smaller thrust verging towards the footwall.
So the basin that I worked on in Syria is an example of a hanging wall vergent inversion system.
Yes, that's it.
Yes, one of the things that has particularly intrigued me on this model is this rather strange fault that goes through the vertical and starts off as a normal fault. But as we trace it up, because it's strongly curved and passes through the vertical, it becomes a reverse fault. But the downthrow side is always on this side.
This is simply an accommodational fault showing the difference in rotation between this fault block and that fault block.
Right. And another of the really surprising things on this model in particular is the way that we get this classic negative flower structure geometry being developed, which is actually within the crestal collapse graben, which has a geometry reminiscent of a positive flower structure. And you could superficially interpret this as the result of strike-slip deformation.
Yeah, these features are characteristic of many of the models which have undergone extension and then inversion, that we get flower structures, negative flower structures and positive flower structures, generated entirely by dip-slip extension followed by dip-slip inversion. To my mind, this means that we have to be very careful in interpreting flower structures because they may not necessarily be indicative of strike-slip, and we need other data to confirm the strike-slip interpretation.
Yeah, it's also interesting just looking at the broader view of all of these models, and in particular the geometries that we get from these Listric models, that they're very similar to the real examples that you've brought along, Chris, the Indonesian example and the Syrian example. And we have a perception that a lot of these major crustal faults are in fact planar, but the geometries that we're seeing on the inverted examples of these faults are characteristic of the models that have the Listric fault shape.
Yes, well, in fact, the two seismic lines from Indonesia are from the same basin and in fact show the same fault about 40 kilometers downstrike, which suggests to me that basin boundary faults may be planar or Listric, but they're fundamentally the same and gradational from one to the other, and the structures that result from them are also gradational.
The third model is designed to simulate the extension and subsequent inversion of rigid domino basement fault blocks. The apparatus consists of metal plates linked together with a trellis system so that they can simultaneously extend and rotate as the model is extended to the right. To begin, the pre-rift sand layers are built up over the horizontal domino blocks. Extension is achieved by pulling the right-hand end of the model away to the right, and the domino blocks rotate and subside. The pre-rift layers drape over the subsiding fault blocks to first form steeply dipping kink bands, which, with increased extension, form extensional faults that link to the individual domino faults. With increased extension, small half-grabens are formed above each domino-bounding fault, and these are infilled with red, black and white synrift sediments. Planar antithetic faults then form in each of the half-grabens. As the model is extended and red, white and black synrift layers continue to be added, the grabens continue to deepen. At the end of 20% extension, a green and white post-drift sequence is added. Inversion is achieved by pushing the right-hand end of the model back so that the domino blocks reactivate and slide back up over each other. As the hanging wall moves back, the extensional half-grabens tighten. The central half-graben is the first to reactivate, with the convex upwards thrust fault propagating up into the post-rift sequence. As inversion continues, a second extensional fault reactivates, producing a footwall virgin thrust in the post-rift sequence. In the pre-rift and synrift sediments, footwall shortcut faults propagate upwards from the tips of the rigid domino blocks. As we approach the end of the inversion, the tops of the domino blocks return to the horizontal, and the model is restored to its pre-extensional length. The synrift wedges in the half-grabens again have arrowhead or harpoon geometries.
The thing that I find very interesting in this model, which we haven't seen in the previous ones, is the way that this allows us to see the deformation in the footwall. We can see a wide variety of footwall shortcut geometries as we look along the length of the model. And in this one in particular, we can see the great complexity that develops as the footwall shortcut process continues.
That's of course possible because the footwall to these fault systems contains a pre-rift sediments as well as synrift sediments in the footwall, and these allow deformation to occur by footwall shortcuts.
Yes, I think that difference between this model and the earlier ones, with the deformable footwall in this one by comparison with the rigid footwall, is a very important point, and certainly something that has this geometry is very similar to the Lulworth crumple. Perhaps we should be interpreting the Lulworth crumple as a footwall shortcut phenomenon.
Yes, I think the Lulworth crumple is related to footwall shortcutting, but to prove it we'd need to be able to put it in its context using subsurface data.
Yeah.
This is a seismic line from a few kilometres to the east, but of course the zone we're interested in is too shallow and too complex to be imaged seismically. What the line does show rather well is how a footwall shortcut fault, which here goes completely flat at the base of the post-rift stratigraphy in green, can separate zones of great complexity and steep dips above from a deeper footwall zone that preserves the original geometry intact.
Yes, I think that this line also nicely illustrates the null point concept. In this area there are two rift events. The upper synrift sequence, coloured in red, is now entirely above the null point. Therefore, its deformation is predominantly compressive. The earlier synrift, coloured in orange, is still just in net extension. The crest of the rollover anticline just returns to its regional elevation. The main fault seems to divide into two branches, as interpreted here. However, the upper branch has no null point. This is because the fault formed during inversion. It did not exist before. Yes, coming back to this model of these domino fault blocks, I wonder if this is quite the right way to model this type of process, because we are making the assumption that the extensional faults have dropped the fault blocks down and then that they've come back up to exactly their original position during inversion. And is this realistic?
We've often seen on seismic data where this does appear to be the case, in the southern North Sea, for example. And on some of the Indonesian seismic lines, the minor inversion structures do appear to have basement restored to a more or less horizontal surface. But I think this is more or less coincidental, and it doesn't have any great geological significance.
And it may be that if the basement does come back to where it started from, we get a good continuous seismic reflector, whereas if it doesn't, it's fragmented and
Yes.
we wouldn't know.
There are certainly areas where domino fault blocks are not reactivated during inversion. For example, in the Western Alps, the contractional deformation is concentrated in the cover, and the extensional architecture of the fault blocks beneath is preserved.
The fourth model is that of a ramp-flat listric fault, in which, like in the earlier models, the hanging wall is first extended and then inverted. Mica has been added between the alternating layers in order to develop anisotropy and enhance layer parallel shearing. Again, red and white synrift sediments are added incrementally during extension. A half graben develops near the upper part of the main detachment. A ramp syncline develops above the steep sector of the ramp. With increased extension, a crestal collapse graben develops above the upper flat section of the detachment at the left of the model. This is followed on the right-hand side of the model by a second crestal collapse graben, which now forms above the flat section of the main controlling fault. Green and white layers of post-rift sediments are added before the inversion phase begins. Inversion is achieved by moving the right-hand end wall back towards the ramp flat detachment. The early stages of inversion are characterized by tightening of the extensional structures and broad arching of the model as compression takes effect. A footwall virgin thrust propagates upwards into the post-rift sequence from the synthetic extension fault in the upper crestal collapse graben. However, the upper listric part of the main detachment is not reactivated. On the right, a hanging wall virgent thrust fault propagates upwards from the crestal collapse graben. On the left, the footwall virgin thrust fault from the crestal collapse graben propagates downwards and joins the ramp section of the main detachment. This still bypasses the upper half graben, and this synrift section is unaffected by the inversion. The footwall virgin thrust fault now forms a tight anticline in its hanging wall. A second hanging wall virgin thrust fault propagates downwards and meets the main detachment at the bottom of the lower ramp. The model is now at its original pre-extension length. However, with this model, we proceed with inversion beyond this point and observe the developments. Uplift becomes focused above the central part of the model, and most of the deformation is taken up on the two outermost faults, giving a large pop-up geometry. Towards the end of inversion, the pre-rift section is thrust over both synrift and post-rift sediments in the upper half graben. The geometry of the faulting in this part of the model increasingly resembles that of a thin-skin thrust, where the faults are parallel or at low angle to the bedding. We can imagine that the geometry of this part of the model, when taken to a more extreme deformation, would produce a nap-like structure, perhaps similar to the cross-section drawn by John Ramsay through the Morkler Nap in the Helvetic Alps.
Analogue modelling has helped increase our understanding of the sort of complex structures that can be developed during basin inversion. We can now feel much more confident in interpreting what we see in such areas and in applying this knowledge to understanding the development of a basin. Of course, whilst we have concentrated on the trap-forming aspects of inversion, our knowledge of the processes involved can be applied to a much better appreciation of all the other elements affecting hydrocarbon prospectivity, such as reservoir diagenesis, source maturation and migration. All of these factors are important to us at the play fairway level, but they are critical to the attractiveness of a single hydrocarbon prospect.